Again,
Awesome.
Steve Senger.
Okay, thanks, Mel. I won't force you to read out the entire title again because that would probably use up most of our time. But we're going to talk about a problem that Mel raised in Cant 2025, and I believe I have a solution, but I will only confidently claim a partial solution, and then we can see what we think about if we can round this thing out. So, first, just I remember Dick Bumby would always come to these talks, so quick picture of him just to think about him for a second because he was always so kind to me, and I know he passed recently. So, uh, here's the basic plan. I want to try to tell you why I'm here, and then I want to prove, sort of state some key results, some key lemmas. I'll prove one of those and then prove the main theorems. And I've also got an illustrative sort of diagram that I think should explain what's going on. And then if there's time, I have a sketch of the proof of the technical lemma, and that's sort of the meat of the paper. It's not particularly hard, but there's just a bunch of geometric arguing that happens, and it's sort of five or six lemmata that are more or less standard on their own, but piling them together and it gets a little wobbly. So if we have time, we'll go into that, and if not, I won't worry about it. And also, I'll make the slides available to anybody who wants them. And this should follow along with the same theorem numbers and everything as the preprint. Um, oh, and I was going to put this on archive, but I figured maybe I'll give this talk, get some feedback from people, and then taking that feedback into consideration, and put it on archive. So we're going to start with some notation. I'm going to let u dot dot v be the interval of integers between u and v. I'm going to use this notation I borrowed from Kevin O'Brien, which is, so if we have this q choose k, that bracket q is going to denote the bracket 1 dot dot q. So this is just shorthand to denote the set of all k element subsets of the first q natural numbers. So we're going to use this so that we can access sort of all k element subsets. And of course, we're going to be mostly dealing with four element subsets today. But just to write that succinctly. Sometimes when I have one of these sets of k elements, I'm going to put a little vector arrow over it to denote the vector whose entries are elements of A. And you might want to quibble about, well, how do we know what order to put those in? I'll just say let's put them in increasing order. If we worry about the order, it could add a constant somewhere, but it shouldn't affect any calculations. So I'm just going to ignore that issue for the moment. Um, and then, of course, why are we here today? Some sets. So if I have a set A that is a set of k, I'm going to say natural numbers, but you can do this more generally, then A plus A is going to be the set of sums, A plus B, such that A and B are elements of my set. And then if I iterate this process in I think, a relatively straightforward way with H copies of A, so A plus A plus A H times, I get what we call the H-fold iterated sum set. So instead of A plus B, I would have A plus C plus D plus dot 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 up to H elements. So I learned from Mel some really helpful way of bookkeeping because I had an idea on this problem, and I was writing notes and sending them to Mel, and then I learned from him a much better way to keep sort of my information organized, which is to write my iterated sums as a dot product. So I'm going to let script x sub hk be the set of all k tuples. So these are vectors of non-negative integers whose entries sum to h. So they could be zero, but they cannot be negative. And these are going to correspond to h-fold sums when I take a dot product and apply it to this vector a. And we'll see that in a minute. I'm going to define this special number m sub hk, which is the size of script x hk. And you can compute this by counting. So I won't go through the details right now, but essentially, the this m sub hk is going to be the maximum size of any h-fold sum set of k natural numbers. For shorthand, for specifically for some of the diagrams, I'm going to be using m sub h to denote m sub h comma 4 because, like I said, we're mostly going to be dealing with four element subsets. So k is 4, I just drop it. The support of a vector is going to be the set of indices associated to non-zero entries. This is just like the support of anything, but sometimes we'll need access to that information. And occasionally we'll need access to the representation function. And so here, what's going on? So if I have some set A, and this is a set of k elements, k natural numbers, then the number of different sums that give me a particular value is going to be the number of ways that I can write that sum. So for example, if I could write a sum as a plus d, but I could also write it as b plus c, then there would be two different of these, I'll call these sum vectors, that give the same sum. And I can compute that sum using a dot product. So this is fairly standard, but it's just a nice way to organize the information. So final piece of notation, if a sum set has maximal size, I'll call it a Sedone set. And more generally, if a set A has k elements and its h-fold sum set has maximum size, I'll call it a B of H set. So B of 2 sets are Sedone sets, and so essentially what's happening is if A plus A plus A plus A is growing maximally, if I don't have overlaps, then I'm going to call it a B of H set. Now I'm going to define script B sub HK of Q to be the set of k element subsets of the integer interval 1 to q that have maximum size. So essentially, BHK of Q is the set of B sub H sets, which consist of k elements and have all of their elements drawn from the first q natural numbers. And the main object that we end up studying in this, that I end up using to study this problem, is this critical or boundary set. So I don't have a good name for this yet, but I've been calling it both. Essentially, I'm going to take the sets A that are B of H sets, but that are not B of H plus 1 sets. So these are k element subsets of the first q natural numbers whose h-fold iterated sum set is of maximal size, but if I compute the h plus 1 fold iterated sum set, it's now got some overlap. So this is, for any set A, it's got some critical h after which things start overlapping and the sum set doesn't grow optimally. Of course, if h is bigger than q, then everything's going to fall apart, but we're going to be keeping h much smaller than q. So what's the goal? Why am I here? So like I said, at Cant 2025, Mel gave a wonderful talk, and there were many things in it, but the thing that caught my eye the most was he showed some computational results about sizes of iterated sum sets. And in particular, what I remember from this talk is he said if he's got a fixed h and a fixed q much, much larger than h, he plotted the histogram of the size of HA for some randomly selected sets. So I can't remember what you did. I think you did like 4-element subsets taken from the numbers 1 to 10,000 or something. And then you just plotted the histogram of which sort of sum set sizes occurred most often. So, not surprisingly, some sets some sizes occurred more often than others. And so, sure. And just by a little bit of thinking, a little bit of thought experiment without being too careful, we think if I'm choosing a small number of elements out of a large set of elements, the likelihood that there's, A plus B equals C plus D, or that there's going to be some overlap in sums is smaller than the likelihood that there are no overlaps in sums. And so it makes sense that the most frequent sum set size is that maximum size. That's what I've called M sub H for, or just M sub H for short. What was bizarre was it appeared like instead of the most likely sum set size, then the second most likely, third most likely, and it sort of seems like it would trail off. There were some spikes, but it appeared computationally, just so empirically, like the gaps between those spikes were consecutive triangular numbers. And this shot sparks in my head because of a project I'd recently finished. So I had this idea of where triangular numbers would show up. So specifically, given an H-fold sumset of a set of four elements, M sub H, that maximum size, was the most frequent. Then M sub H minus 1 was fairly frequent. But then it seemed kind of rare to get M sub H minus 2 and M sub H minus 3. But M sub H minus 4 shot up again. And then it dipped for a while. And so today I'm going to claim that these first two triangular gaps must occur, again, for fixed H and Q with Q much larger than H. And I believe that we can extend this, use this same argument to extend and show that at least the first H gaps uh, must be triangular as well. But that's a conjecture, so we'll talk about the conjecture later. And I have to say explicitly a whole lot of thanks to Noah Kravitz, Mel Nathanson, and Kevin O'Brien, all of whom have tolerated a lot of discussions with me, both on email, in person, over Zoom, and all sorts of things. So I'm very grateful to all three of these guys for extensive conversations. And I also have to give a shout out to Paul Baginski, who has heard me talk about this problem, even though we haven't maybe discussed it too much in the nitty gritty, but he's heard me talk about this problem for months. Um, so that was the introduction. Now I want to move on to the results section. And this is going to be kind of the main ideas. So I'll do the main statements, a little bit of proof, and then I'll kind of pause there, and then we'll get into the technical proof if there's time or interest. So how are we on what's the question? Also, I have a helpful graphic that'll show up at some point too. We okay with what's the question? Because it's a little weird, right? We take four element subsets, compute iterated sumsets, and then look at the histogram, like why would one do this? There are lots of good reasons to do this, but then triangular numbers in particular, where did those come from? So I hope to explain this phenomenon and argue that it must happen the first two times and then that it should happen from there on out. Okay, so here's my technical lemma. So at the top, I've reminded you the definition of script B sub HK and script B star sub HK. So this just means the B sub H sets, and this means the sets that are B sub H, but not B sub H plus 1. And in most of this discussion today, K is going to be 4, and we're going to be dealing with just the first Q natural numbers. I'm thinking Q is some, millions, billions, trillions, and H might be like a few thousand. Okay, so here's the technical lemma. And a comment on the presence of H here. I don't think you have to work very hard to get these without careful reliance on H, but I wanted to track the reliance on H because if this particular approach doesn't work, maybe having some quantitative control on how various quantities behave with respect to Q and H could help. So what do I say? If Q is large and H is at least 2, then we have that the size of this B sub H star, this is this critical or boundary set, is bounded above by a constant times H to the 7th Q cubed. It's bounded below by a constant times H to the minus 5th Q cubed. And so those are upper and lower bounds. Those are kind of giving me, if I ignore H, that's saying that for every H, B star of H is Q cubed. Since I'm dealing with four element subsets, I know that for every H, the B of H size is Q to the 4th. I haven't proved that yet, but we can show that. And now I'm saying that those sort of boundary sets for each H, I'm clipping off a proportion of Q cubed. Now, this third statement is a little bit more technical. This third statement says the elements in B star H whose H plus 1 fold sumset is of size less than the max minus 2 is bounded above by H to the 13th Q squared. So what are these first two saying? They're saying the number of boundary elements is at least Q cubed, or is proportional to Q cubed. And now this is saying the number of boundary elements that, moreover, are off by more than 1 is Q squared. So this is taking for each H the B of H sets that are going to be B of H plus 1 sets, the B of H sets that are not going to be B of H plus 1 sets. Then from those, we've got Q cubed of those, and Q squared of those are going to disappoint us. They're going to shrink much faster than expected. Okay, so that's the technical lemma, and we'll be using pieces of this, and I'll be reminding you of them as we go. This is what I've called the gap lemma, and this was sort of the main observation that I believe I sent in a fever dream email to Mel, typed out on my iPhone, and he said, "What are you trying to say, Steve?" And I said, "Maybe I should tech this up." So in this language, so again with the same notation for calligraphic B and calligraphic BH star, what I'm saying is those critical or boundary sets have this nice property. So if A is a B of H set, but not a B of H plus 1 set, then I can show that B of H plus I, A, so that is the H plus I fold iterated sum set, is going to be bounded above by M sub H plus I minus I plus 2 choose 3. So what this is saying is once I know that so if A is a B of H set, but not a B of H plus 1 set, once it crosses that threshold, I can quantify, give an upper bound with how big its iterated sum sets, its further iterated sum sets can be. Moreover, what you're going to notice is as we increment I, we're getting consecutive tetrahedral numbers whose differences are, of course, consecutive triangular numbers. And I'll make that more explicit in a moment, but just to state clearly two pieces, I have theorem 1 and theorem 2. Theorem 1 is, again, given Q sufficiently large with respect to H bigger than 2, the second most frequent size is the maximum minus 1. So the most frequent size is the maximum size, and this has been known for a long time, but we'll show that calculation. The second most frequent size is the maximum size minus 1. So I'll prove this using those previous the lemmas 1 and 2. Theorem 2 is a bit more technical, but it says again, given appropriate Q and H, the numbers of elements whose this should be numbers of elements whose H-fold sumsets. I'm missing the phrase. This should say whose with H-fold sumsets of sizes M sub H minus 1 and M sub H minus 4 are at least something times Q cubed, and the numbers of elements with H-fold sumsets of sizes M sub H minus 2 and M sub H minus 3 is bounded above by Q squared. And I've got a picture to illustrate this in just a moment, but let me say that putting these two together, along with the fact that the most common sumset size is the maximum, and that happens at roughly Q to the 4th times, this is going to give me that the first two gaps between H-fold iterated sumsets have to be 1 and then 3. So here's a photograph of the whole situation. I'm going to try to see, can I still use the laser pointer? Annotate. I think I can just use laser pointer. Okay. I cannot use laser pointer. My computer doesn't want me to use the laser pointer. That's fine. So what is this saying? Well, I've got this color coding here. So I've said
division. If New Yorkers vote, I win. What we want to do is just make sure New Yorkers know how important this election is and what's at stake.
Okay, thank you. So what I'm saying here, I have three sorts of sets that I'm sort of counting here. So I have B sub H sets. These are sets that are B sub H, and those are given by the black block here. These are the B sub H sets. Then I have B sub H minus 1 star sets. So these teal sets are, so here, 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 and here.
They are the ones that have just started to fail to be see them like.
Yeah, so
and over there you don't see the spike. The spike is coming from the ones that failed one stage ago, and they're now failing a lot more, and that's what's contributing to the spike.
Correct. That's the punchline of the talk. You win. That's it. Essentially,
I just wanted us to see that I understood what the picture's saying. Yeah. No.
That makes me very happy. I'm very grateful because I'm like, I've been talking about this for a while, and I'm afraid I'm not doing a good job of communicating it. So I'm really grateful this has made sense. So basically, yeah, exactly what Moshe said. These are the sets that are B sub h minus 1 sets, but not B sub h sets. And what we're going to see is that they are most likely to be here. They're most likely to be 1 off of the max. And that is why this is above q cubed. Again, there are constant multiples here. This is a picture. It's not a histogram or a measure of anything precise. Then the other b star h minus 1 sets are going to contribute less than q squared. So since q is much, much bigger than h, I can see biggest contribution, q to the fourth, are the b sub h sets. But then the sets that just failed at stage h, but were b sub h minus 1 sets, most of those end up here with a little bit of stuff here. Okay. Then going another stage back, the b sub h minus 2 sets. So these are the sets that were b sub h minus 2, but not b sub h minus 1. I look at their h minus 2 fold sumset, and I've got, again, q cubed of them, but I do not have, they by that gap lemma, could not contribute sizes here. So by that gap lemma, the largest size they could contribute would be maximum minus 4, or something smaller that I've not drawn in this image. So this is the basic picture. Let's see if I can now continue.
Just without meaning to pre co-opt you too much. The you figure the next spike is coming from BH minus 3.
That's what I claim.
I mean, it would be a minus 10. It's happened to M of H minus 10.
Precisely. And
okay.
that's where I claim those, because it's happening at every tetrahedral number, and the gaps between those are triangular. That's exactly what I think is happening here, yes. And moreover, this is quantitative because I'm saying sort of rare things happen less than a constant times q squared, and I'll say frequent things happen more than a constant times q cubed. And just to point out, Kevin had noticed with some experimental results that this spike appeared to be shorter than this spike. And again, I don't have a solid proof here, but I think if we keep track of H and the asymptotic effects of H, we'll see, well, this spike can have a contribution not only from B sub H minus 2, but also some contribution from B sub H minus 1, which is why we're getting a slight jump up. That's still conjecture. But now I want to tell you sort of where each piece comes. So this next diagram will get messy. So this is going to be from lemma 1 and 2 when I'm looking at the h minus 1 fold sumsets. That is, I'm going to say it's at least a constant times q cubed, and at most a constant times q cubed. The height of this bar is going to be from, again, lemma 1 parts 1 and 2, but applied to the h minus 2 fold sumsets. And same basic idea, and lying a little bit because I'm stacking these two blocks on top of each other. But then the proof that these have to lie below the q squared line, or some constant times q squared, is going to come from lemma 1 part 3 applied to h minus 1. And as I said, the reason that the h minus 2 piece is starting all the way down at m minus 4, that comes from lemma 2. So this is sort of the picture of the argument without, if you assume that the lemmas 1 and 2 are correct, then this is sort of how I'm arguing that the first two gaps must be 1 and 3. Again, gap meaning gap between scores whose histograms are greater than q cubed, or sumset sizes whose frequency is greater than a constant times q cubed. So to the extent that this can be understood, is this tracking all right for folks? Because this is like my central diagram, but if there's anything here that's completely nonsensical, just let me know. Because we're going to be getting into
Looks good.
Yeah. Okay.
Seems fine so far.
All right. Thank you. So now, I got something in the chat, which is, yeah. All right. Thank you. So now let's dig into the nitty-gritty a bit. So I want to try to prove theorem one. And I made a decision when I was writing this initially to look at the h plus 1 instead of h to make certain expressions simpler. In a future draft, I might roll it back because this could end up confusing folks. Feel free to let me know. Basically, I'm going to look at b sub h minus 1, and I can write that as the sets which are b sub h sets, uh, b sub h plus 1 sets, set minus the sets which are not b sub h plus 1 sets. So that makes sense. These are the b sub h plus 1 sets. But luckily, this is a disjoint union of sets which are only b sub 1 but not b sub 2. That would be b sub 1 star. Sets which are b sub 2 but not b sub 3, which is, of course, b sub 2 star, etc. And so that's how I get this union. I'm going to apply lemma 1.1, that is the upper bound, for each of these sets, and I get that the size of b sub h plus 1 is at least q choose 4. So here this is honest to God a binomial coefficient, not a set, minus the sum of each of these. Now this is a big O statement. I've not computed exactly what this is, but for each b sub I star, I know it's no bigger than I to the 7th q to the 3rd. Well, if I sum up h of these, and I'm very lazy with my summing, but I'll get something that's on the order of h to the 8th q cubed. And again, if q is much, much larger than h, this is still big theta of q to the 4th. So I've shown that the number of b sub h plus 1 sets is still q to the 4th. And this is equation 1. We'll come back to equation 1 later. Now appealing to lemma 1 part 2, so this is where I was saying, like, I'm going to get that lower bound. I'm claiming that in BH star, there are at least q cubed over h to the 5th sets. Again, I haven't proved lemma 1 part 2. I'm just appealing to it. And each of these will have size smaller than the maximum minus 1. So what have we done so far? Go back to the diagram. We've shown that for b sub h plus 1, this part is q cubed. And now we've shown this part is at least, sorry, this part is q to the 4th. And now we've shown this part is at least q cubed and at most q cubed. So then we look at those sets with size strictly smaller than the maximum minus 1. And this is where we appeal to lemma 1 part 3. And that tells me, okay, I've got less than q squared sets down, giving me smaller scores. So the most frequent size is clearly of the order q to the 4th. The second most frequent size is clearly of the order q cubed, and the other sizes are going to be on the order q squared. Now that I say this, I feel like I'm contradicting what I said about that third spike being higher. So there is a problem. Okay. There's a slight issue here. This shouldn't be, I think it's just in the phrasing, second most frequent size. But certainly the biggest two, if I'm looking at the first two, the biggest two are the biggest size, the biggest minus 1, and then the next two sizes are smaller. So for sure, that first gap between frequent sizes is 1. This should be the proof of theorem 1, although, like, I'll admit this phrasing is a little unhelpful. This is technically inaccurate phrasing. But the claim here is that we've got this is q to the 4th, this is q to the 3rd, and these other contributions are smaller. So now let's move on to the proof of the gap lemma. And so now we want to look at even smaller scores. How do we get a hold of that? And this, to me, is sort of the key of what's happening. This is sort of the reason this thing works is because when I'm missing, if I have maximum expansion, that is, if I have maximum size, B of H set, everything's grand. And then as soon as I'm no longer a B of H set, there's some repeated sum. There is a repeated sum at least, maybe more. And for each repeated sum, when I iterate the sum set again, that begets many more repeated sums. And each of those then produce even more repeated sums, and that's why we're getting this rapid decay here. So a loose proof of this, like a sketch of a proof, suppose I have a set in B sub h star. So this is, again, this is a B sub h set that is not a B sub h plus 1 set. I'm going to suppose the four elements are in increasing order A, B, C, and D, and I'll suppose that A has maximal size. You know, it's a B of H set, so it's going to have maximal size. However, since it's in B sub H star, it is not a B sub H plus 1 set, meaning the H plus 1 fold sum set is going to be off by at least 1. It'll be less than this, so it's less than or equal to the maximum minus 1. So if I ignore repetitions due to permutations of terms, namely, I know A plus B equals B plus A, but if I ignore those kinds of repetitions, I mean that there's going to be at least one pair of sort of meaningfully distinct sums of H plus 1 elements that evaluate to the same total. So I'm going to call these elements F and G. So, and I'll do an example of this in just a moment. So I'll say F is a linear function of A, B, C, and D. G is a linear function of A, B, C, and D. And somehow they sum to the same value. And I could think about this, the F and G, I could think about these as having coefficients who correspond to the entries in my sum vectors. So for example, if H is 2 and A is the set 1, 2, 8, 10, I can check that A is a B of 2 set. So if I, B sub 2 set, if it's a Cedon set. If I check all the pairwise sums, they'll be distinct, and I'm very happy. But I notice it's not a B of 3 set, as I have 1 plus 1 plus 10 equals 2 plus 2 plus 8. So in this case, if this is A, B, C, D, what I'm saying is F of A, B, C, D is 2 times A plus D, and G of A, B, C, D is 2 times B plus C. So we get 12, two fundamentally different ways. Again, it's not like A plus D and A plus D plus A or some permutation of the same elements. Like these are fundamentally different sums. Okay, so F here would correspond to the sum vector 2, 0, 0, 1, and G would correspond to the sum vector 0, 2, 1, 0. And so you can see if I treat this set written this way like a vector, if I dot this vector with this vector, I get exactly this sum. And if I dot this vector with this vector, I get exactly this sum. So this is, again, just to show you how the vector notation for iterated sum sets and what it means to have a collision. I've got two distinct sums that equal the same thing. Okay, so now I had an I had a B of H set, A, and in the H plus 1 fold sum set, there was at least one collision, maybe more, but at least one collision where F equals G. So now I look at the H plus 2 fold sum set, and I claim it can be of size at most maximum minus 4, because even if all of the other sums are as distinct as possible, that would only increase it. But if those are as distinct as possible, I still must have, since F equals G, I have F plus A equals G plus A, F plus B equals G plus B, F plus C equals G plus C, and of course the same thing with D. So now instead of missing just one, I'm missing 4. And you might say, well, did you keep track of that 1 from the previous size? No, 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 because now we're looking at M sub H plus 2. So this is the maximum size of an H plus 2 fold sum set, and I've got to be at least 4 off of that. Now continuing, if I look at the H plus 3 fold sum set, I'm going to be off by 10. And why is that? Because now I have 5 choose 3, that is 10 choices for pairs of elements added to both F and G. So here I added A to both F and G. Now I'm adding A plus A to both F and G. Here I added B. Now I've got A plus B, A plus C, A plus D, etc. And there will be 10 such pairs. And in general, when I get to the H plus I fold sum set, iterated sum set, I'm going to be losing I plus 2 choose 3 of these sort of what I would consider sort of downstream effects of just having F equals G at that H plus 1 fold sum set. So H fold sum set's maximum size, H plus 1 fold sum set, we're missing 1, but then missing just one sum there causes this sort of chain reaction where we miss consecutive tetrahedral numbers with each iteration. So that's the proof of the gap lemma. And it looks like I got some chat. So triangular numbers are important because they're triangular. They're important because they're. That's one interpretation. That's one interpretation. Yes. For me, the triangular numbers showed up because of a sort of a similar thing that happened in a different project, and that's why I was so latched onto this. So the last big thing I want to do is the proof of theorem 2. If, oh dear, if my computer allows it, there we go. It wasn't letting me switch sides for a minute. And to get to this, I want to start quantifying what I've called H frequent and H rare sumset sizes. And this is basically, is it, big O of Q squared, or is it big omega of Q cubed is going to be these dividing sides. So the triangular gaps appear in the frequency of these sizes of HA because this phenomenon happens at different values of H for different sets A. So each A belongs to a unique B star H. If it belongs to B star H, it's not going to belong to B star H prime, right? That's that critical H value for which it is a B of H set, but not a B of H plus 1 set. And I should notice or mention all sets are B sub 1 sets because it's just A is just A. Its maximum size is just 4. So the critical H could be 1, but every set has some critical H. Now, if I fix an H greater than or equal to 2, I'll call this potential H-fold iterated sumset size H frequent if it occurs, omega Q cubed times, or H rare if it occurs big O of H squared times. I think in Mel, I think in the draft I sent you, I actually accidentally put H cubed, Q cubed here, which was a typo. So the math bears out that I want Q squared here, but I think there was a typo in a previous draft I sent. So basically, the largest size is going to happen Q to the 4th times, so that's considered frequent. It is bigger than Q cubed. But those rare set sizes are going to occur less than Q squared times, or, again, within constant multiples. So to prove theorem 2, and this is kind of the engine that I would expect could prove the whole thing. But what do we say? By theorem 1, the most likely size is the maximum size. And again, this second most likely is not helpful notation. So second most likely from the first 4 being 1 off of the maximum. And that comes from the B sub H plus 1, B sub H minus 1 star sets. So these are the sets that are B sub H minus 1 sets, not B sub H sets.
Just checking the second spike in your picture going from right to left was actually larger than the middle spike, right? So this is second most likely is actually technically not correct, right?
Yes, that's where I realized I was using sloppy language here. So second,
what you mean is the set is going from from the largest going down, going from right to left in your diagram, the second spike. Yes.
Yeah, the second spike. And that's why I've used this oh goodness. I've got this notation of frequent and rare, but I should have said the second frequent spike rather than the second most likely. This is awkward wording, so I apologize for that. Yeah, so technically speaking, this is imprecise, and the statement of theorem 1 is also imprecise. So I apologize for that. This should say, yeah, the second frequent, not most frequent, yeah. So then quantitatively, we see that both of these are H frequent sizes. You can just apply the lemma 1 parts 1 and 2, and you see these are both H frequent sizes. But in particular, that equation where, and I'll flip back to it, but this was the equation where we estimated the size of a B sub H plus 1 by taking the B sub H plus, let me just go back to the equation because now I've swapped with H and H plus 1. We're looking at the size of the number of B sub H plus 1 sets by taking the sets which are B sub H plus 1, and we're subtracting off those which were not B sub H. And I guess this is all not B sub H because these are going to be B sub 1 star. So those are the sets that are only B1 and not B2. plus B sub 2 star, which is the sets that are only B2 and not B sub 3, etc., up through H. So this, if I catch back up to where we are, I probably should have just copied this equation down here. So in particular, 1 guarantees that there are q to the 4th sets of maximum size, and all others occur fewer than q cubed times altogether. And this is with h to the 8th instead of h to the 7th because I'm counting it very grossly. So any set A with size strictly smaller than the maximum minus 1 will either be in a B sub h minus 1 star, or it won't. So it'll either be a B sub h minus 1 set, or it won't.
Well, you said that -2 and -3, it can't possibly be anything other than B star h minus 1, right?
Correct. That's precisely
That's why they're the rare ones.
Yes, that's exactly correct. So by lemma 3, we know that the sets of sizes max minus 2 or max minus 3 or smaller are going to occur no more than q squared times. Okay, so if it was in the B star h minus 1, then we've already got a bound on that by lemma 1 part 3. Now, if it was not a B sub h minus 1 star, well then for some h bigger than 2, it must have been in B sub h minus I star somewhere. So if it was not a B sub h minus 1 set to begin with, then it must have been a B sub h minus something else set. And from the gap lemma, we know that it can be no bigger than the max minus 4. So from this, any set that has size less than the maximum minus 1 is going to either be, if it's one of these critical sets, it's going to be small by lemma 1 part 3. And if it's not one of these critical sets, then by the gap lemma, it's got to have size smaller than max minus 4. And so this I'm very confident in. And what I believe is we could continue arguing to show the rest of the gaps are triangular, but we'll hold off there. So by lemma 1 part 3, we still have now I'm confused. I want to say there are these choices that have not been dealt with. So I apologize, I'm confused by this slide now. There are at least.
Sorry, I've lost track. What's theorem 2 now? I'm sorry.
Yeah, no, I'm sorry. This is what I get for putting theorem statements far, far away from their proofs. So theorem 2 says that the maximum size, the maximum minus 1, and the maximum minus 4 are frequent. That is, they occur at least a constant times q cubed times. And the sets that are the maximum minus 2 and the maximum minus 3 are rare. That is, they occur less than a constant times q squared.
You've already described why 2 and 3 are rare, right?
Yes.
So what you need to do now is explain why 4 is common again.
Yes. Thank you. Oh, goodness. Yeah, I should have restated this. So we have that, we have this, and then so we said something is confusing me here because lemma 1 part 3 does not have this. I think this should have read lemma 1 part 2 because the lower bound should have been lemma 1 part 2. So I believe that this should be lemma 1 part 2, not lemma 1 part 3.
Okay.
This threw me off, so I apologize. This is a typo. So there are still at least q cubed choices for A that have not yet been dealt with. And so there must be that many A in the B sub h minus 2 set. Oh, could I please move forward? Let's see here. So this is where we've shown we've taken some, so we've got q cubed choices left over. Well, then those must be B sub h minus 2. And I know by lemma 1 part 2 that there are at least q cubed of those. So I have at least q cubed at each of those spikes between triangular numbers, and they've come from maybe earlier uh, iterated sumsets. So in this case, h minus 2. But basically, this is saying we have the largest spike must be there. The second large spike, which is not the second largest, the second large spike must also be there. Then we showed the next two spikes must be small. And now finally, we've shown that the spike at maximum minus 4 must also be greater than q cubed. So we've carved out q cubed. Let me sort of try to explain it with the diagram again.
The lesson is that when sort of, I don't know what the word would be, HC donicity fails, it fails by 1 as a rule. And
Yeah.
from there on, the failures grow mostly like increasing by the triangular numbers. And there are other cases where the failure is more than that, but they're rare.
Correct. That's a
Okay.
great way to put it.
Okay.
Yeah, so essentially we get this is known that the biggest spike is bigger than q to the fourth, and we have a calculation of that here just for completeness sake. And then by lemma 1 parts 1 and 2, we get upper and lower bounds on, like you say, failure by 1. So failure by 1 happens very often. Failure by more than 1 is quite rare. Now, if
And
this
when we say failure by more than 1, we mean at the point where it first fails.
yes, so
If it fails, the point where it first fails, it fails as a rule by 1. After that, it's going to fail more and more in a predictable way, at least
yeah.
a predictable way.
Yeah, and that's by the gap lemma says, it's going to have maximum possibility of showing up here. But then by applying lemma 1 parts 1 and 2 to the fewer iterated sumsets, we still have there must be q cubed elements that failed. These were in b sub h minus 2 star. So then when I do 2 more iterated sumsets with these, well, now they're off by 4 instead of being off by 1. And then, of course, down here we would have more teal and pink contributions, which are below q squared. And that's like the main point of this. So that was the main idea. I apologize for a couple of very confusing typos. Um, and that explains the first two triangular gaps. And then the reason I think this should keep working is I think you can just keep going and saying, well, then look at the h minus 3 critical sets. Well, those are going to occur. There have to be q cubed of them that have size maximum minus 10. And then anything from b sub h minus 3 star is going to contribute fewer than q squared. And so we look at, well, what are the contributions here or earlier from b sub h minus 1 star and b sub h minus 2 star? And what we see is those contributions are all less than q squared. So we have necessary spikes at every tetrahedral number by lemma 1 parts 1 and 2, and then we see that the gaps in between must be small by lemma 1 part 3. And there's this problem of mixing, like as you go far enough out, how do I know that maybe those q squared tails don't like conspire against me and clump up to be bigger than q cubed?
You
And
need better control of your constants, I guess.
yeah, and so that's why I put in the explicit values of h there, so I can see how h grows, how h affects those asymptotics. And as long as q is big enough with respect to h, so as long as q is much bigger than say h to the 13th power or whatever we end up with, then I believe this should just bear out. So this is essentially what I just said. So then if this conjecture is true, that is, if I have that these are the h frequent sizes and the others are h rare, again, as long as I is less than h, then the most frequent sizes should be these maximum minus tetrahedral numbers. And of course, successive tetrahedrals have gaps which are triangular, which would explain the triangular gaps. And this appears to follow, like I said, from lemmas 1 and 2, but it certainly, maybe I'm bold and arrogant, but not bold or arrogant enough to claim this with certainty today. So I'm sort of curious if anyone sees a glaring problem with that claim. But basically, I need to check the asymptotics with H and make sure that there's not something like after maybe like logarithmically many steps, it blows up instead of for all the way out to H steps or something. But that's sort of the main those are the main ideas. And then so in the whatever time or interest we have remaining, I can talk about the technical lemma. Um, and also, Mel, when would you like me to stop? What time?
Uh, Whenever you want to. In the virtue of a Zoom seminar is that people can sneak away unnoticed if they
Okay.
are so inclined.
Well, I'd like to give some sort of flavor of this, but also give people if people have like, sort of questions, maybe I'll try to give an idea of this in 5 minutes and then leave 5 minutes for questions.
Okay, so let me first thank Steve for the first part of his talk. And we can now start the technical lemma part of the talk.
Yeah, this is where we get lost in the weeds. Um, but this is where some of the notation I introduced earlier. Ah, thank you. Um, Basically, and I'll just brush through this rapidly. I'm going to be thinking of the sum vectors as vectors in Z4, and I'm going to be thinking of the sets as vectors in ZQ to the fourth. So I'm looking at lattice points in 4 dimensions. So what are these borderline sets? These are sets where for all H sum vectors, we have distinct dot products, but then there must be some pair of H plus 1 vectors where we have dot products that line up. Well, if you've ever glanced at my CV, which I don't necessarily recommend, probably 50% of it has the word dot product in it. So almost half of my talks, I say the word dot product. So when I saw this connection, I was very comfortable. And well, when are dot products constant? They're constant along hyperplanes. So if I fix one of these sum vectors and I fix a dot product, the sets which give that dot product somewhere are going to live on a hyperplane. And the rest of the proof is looking at intersections of hyperplanes and drawing conclusions. So in particular, and this is sort of one of the exciting things to me because this is where the geometry and the number theory really play against one another. So if I have a set A in BH star, then for any pair of vectors in the H plus 1 sum vectors, if they give the same dot product, they have to have disjoint support. And if they have disjoint support, they are therefore orthogonal. And basically, it just comes from the definition of BH. So if they didn't have disjoint support, then A would not have been a B of H set. And this bears out just from writing down what these things mean. And you get a lot that follows from that. So I wrote this lemma, and actually Mel wrote a shorter, clearer, more general version of this lemma. So, but a corollary of this lemma, the lemma is actually different. This is a corollary of the lemma, which says if I have something in BH star, then there are at most two sum vectors that have a fixed dot product. And this is something about how many distinct dot products are possible. It actually requires a little bit of work to show. So the upper bound is trivial, but the lower bound requires maybe a little bit of thinking. This says if I have two vectors with disjoint support, which is the case that I'm working in, because if I'm looking at B of H star, then I can have at most Q cubed points on any of these hyperplanes. And it should make sense because a hyperplane in 4 dimensions is going to have about Q cubed points on it. Now I'm looking at the intersection of two of those. So since these are orthogonal, they're linearly independent, X and Y are, which means the intersection of those hyperplanes has at most Q squared points on it. But then I multiply by the about Q different possible dot products. So that's where I get this upper bound. Essentially, that's where this upper bound part 1 comes from. Then part 2, I've got a constructive proof. Noah gave me a proof that is not constructive but didn't have control on H. It's just, there's some factor of H. So I constructed a set, and I was so excited, and I emailed Mel about it. But I constructed a set. So somewhere inside of the set of four element sets, we have sets that give me B star H. I can construct Q cubed many of them, albeit with a bad behavior on H. Finally, and this gave me a scare last night because as I was typing up these slides, I realized I had something that was correct, but I had left out a sentence as to why. And so around midnight last night, as I'm putting together, no joke, the last slide, I said, "Oh my gosh, what if this whole thing is wrong?" It's not wrong, it's fine. But basically, this is looking at intersections of four hyperplanes because this is what, how do I miss more than one? Like as Moshe points out, that as a rule, we're just going to lose one sum. If we're losing more than one, something really peculiar is happening. And so what peculiar thing is happening? Well, a consequence of one of the earlier lemata is that I can't have three hyperplanes intersecting meaningfully. So now what if I have two pairs of hyperplanes intersecting meaningfully? Three hyperplanes with the same dot product. So now I could have two pairs with distinct dot products. This requires a little bit of work to show that no triple of the vectors are linearly dependent. It's possible that the four of them are, so there's some symbol shoveling involved. It's not horrible, but it's maybe half a page of doing linear algebra. And so when you do this, you end up with indeed this can only happen if there's some really rare geometric thing happening. And so we count how often that happens, and we get quantitative bounds. This little sentence here, oh my goodness, that was terrifying last night. I forgot about that. These choices fix the second dot product. I thought, oh my gosh, I'm off by a factor of Q. I'm off by a factor of Q. Everything falls apart. No, it's fine. Once you've fixed all of your vectors and one dot product, that uniquely fixes the other dot product. Sorry, all of your vectors, all the sets, and the dot product. Then it fixes the last dot product, and that is it. Here are some relevant references.
And let's thank Steve again for part 2 of his talk.
Many thanks.
No, thank you all for coming and paying attention. I'm very grateful.
Let's see, comments or questions?
It doesn't seem to have anything wrong with it.
Yeah,
Whatever it's
nothing's
worth.
wrong. Yeah. Why four element subsets? Is it because three elements are kind of easier? But you do suspect same behavior for more than four, right?
So I think Mel could probably give a better answer, but I'll say if I have some comments on this as well. If you do like 5-element subsets, then it looks like you're getting whatever they're called, pentatopal numbers whose differences are polyhedral numbers. And so I'm guessing what Mel did some work on the 3-element subsets. And so if you look at the distinctions between triangular numbers, then you're getting like an arithmetic progression or something. So maybe it just didn't appear that interesting. Mel, do you have a comment on that?
Yeah, I guess, or to be more precise, I guess I should. So if you're looking at twofold sumsets, there's like the smallest possible size and the largest possible size. And in fact, you can get every possible size as a sumset size from the smallest to the largest. But then if you look at threefold sums, so this was actually the initial observation that created this set of questions between the smallest sumset sizes, which always come from arithmetic progressions, and the largest, which are these, sit-on type sets. There were lots of missing sumset sizes, and when I started to look, I was just doing a lot of numerical experiments, letting Maple run crazy. And then, because I just wanted to see what were the missing sumset sizes. And then for some reason, I decided to plot the frequencies of the ones that occurred. And you end up getting like a graph that looked like something you saw in freshman physics when you were looking at like the absorption spectra of some molecule or other. You get these peaks. So I thought these were really beautiful pictures. And and then I saw that in this first case, the differences between the successive peaks were triangular numbers. And if you look at higher sum sets, you get the similar phenomenon, everything like moved up one level geometrically. Uh, and just as in between these two peaks, between two successive peaks, you'll get the same phenomenon of peaks, but you won't see them unless you're very careful about what you're looking at because the endpoints are so big. Like you don't see these peaks at all if you do like this histogram thing, because almost every set is a sit-on set. Uh, so what you see is just no peaks at all. You see like a horizontal line and then it jumps up to almost everything. But then if you take away the maximum one, the sit-on set one, and you do your histogram, then you see these peaks. So I expect that this phenomenon is iterated forever as you take higher and higher sum sets. But life is short, and there are lots of different things to look at. But this is like the start of this kind of investigation. And then I got distracted by Hilbert polynomials and such things. So, you know, it's hard to focus on one thing. Well, actually, it's easy to focus on one thing, but when my attention gets distracted by another thing, then I just focus on that, and I forgot or put aside everything that came earlier. But they're already so there several papers that I have on archive about this, and on the subject of these triangular gaps, Kevin O'Brien has a paper that's on archive, and Noah Kravitz has a paper that I don't think is on archive, and I don't even know that it's a paper. It's just maybe just some notes that he sent me, but the experimentally observed phenomenon is real. It's not just an accident of the sets that were randomly selected to study. Fortunately for me, several other people got interested in this, like Steve. So there's significant progress. Oh, Steve, one very minor point. In the preprint you sent out, I assumed that you put the references in, as in the slide here, alphabetical order.
O-N. Oh, great. I'm still learning, Mel.
Now I was thinking maybe it was like B comes before N, but I don't know.
Yeah, yeah, maybe I thought K came before M. I really don't know what happened there.
It's like another author on this subject is a French mathematician whose last name is D. Roton, D-E space R-O-T-O-N. And I had to ask her whether in a bibliography the first letter of her last name is D or R. So
And what did she say? Do you recall?
no, but whatever she said, that's the way I set up the bibliography, whatever paper it was. So whenever I put, so if you see it in a paper of mine, it's in the correct order.
Okay. Well, I gotta say this was, if nothing else, a whole lot of fun to work on because I got to relate an old project of mine along with one of my favorite topics, which was dot products, and finally got to do some number theory. So
What was the old project that?
this was the thing I spoke on at integers about the planar function bound. So you have these functions that have some equalities, and the essential thing to notice is that if f of a equals f of b and f of b equals f of c, then by transitivity, f of a equals f of c. And those occur with, sort of only triangular numbers of equal signs can occur. And it was a similar sort of restriction. So once you see the triangular numbers appear, or the n choose 2 appear, you're like, aha. And so it restricted some number theory, and we got to wrangle it and get a nice world record bound. So
Let's see. Oh, I'm sorry. I should have, damn. Where is this? So can you close out your slides?
yeah.
And before,